Hey everybody, I'm going to do a quick recap video for some of the things that we experienced in the lab and learned in a more traditional sense, and as well as expand on some of the things and look at where we're going to go at the end of this week. The first thing we saw was Boyle's law, which is an inverse proportion with pressure as it relates to volume. And to show you what I mean, let's allow this piston to freely move. And so let's say that we have a certain volume. I want to look at what happens to the pressure if the volume either increases or decreases. So if I decrease the volume, come on now, look at what happens to the pressure. I think I was at, I don't know, 570 or something like that initially, and then I changed the volume to 210 and the pressure increased accordingly because I decreased the volume. And the way that we're going to measure pressure is the impact of little gas particles with the walls of a container, the force they generate in a given area. When they have less space to freely move, they're going to be more restricted. And if you guys recall from the kinetic molecular theory, gases have higher kinetic energy than both liquids and solids by nature, which means they move more, and there's more space between the representative particles. So here I've decreased the volume, I've increased the pressure. When I increase the volume, pressure goes way down, because now there is more three-dimensional area or space for a gas particle to move freely. Let's look at some other examples of different situations. Is it possible to control temperature? And what might that do to volume? Now, again, I'm going to allow this piston, stop. I'm going to allow this piston to move by clicking this unlock button. I'm going to heat this up. The heat supplied causes a rise in temperature. And as we know, temperature is only a measurement of kinetic energy. So as you see, when I heat this, the volume is going to expand. Conversely, if I cool it down, which is just a very lame term for removing kinetic energy, if I have something with a lower temperature differential, I'm going to cause that volume to decrease by nature because the particles are moving less and less. So that was Charles' law, the representation of volume and temperature. And we did a lab where we put a sealed syringe in boiling water versus cold water. And what we should have seen there is any increase in temperature leads to a direct increase in volume and vice versa, which is a proportion. What we haven't talked about yet is very similar to Charles' law. It's called Gay-Lussac's law. And the only difference here is in Gay-Lussac's law, let's assume for a minute this piston is sealed. It doesn't have the freedom to expand or contract with any different changing conditions. But I can still do the same thing with temperature. So heat this thing up, and when this is now locked in place, we have a rise in pressure. When I cool it down, we have a decrease in pressure. And so you would still see the same type of relationship, except the only difference between Gay-Lussac and Charles' law is that we have substituted volume for pressure. Gay-Lussac's law is more applicable in a sealed container. And that's going to be the major distinguishing characteristic here. It is more applicable for sealed gases. And what I mean by that is, let's say if it's a syringe, I'm going to lock the plunger in place. It wouldn't be anything like a balloon where the gas is free to expand and change in volume with changing conditions. Gay-Lussac's law strictly deals with fixed volumes. So unable to change the volume, but I'm now going to account for a change in temperature, which can also change the pressure. And so we haven't discussed this one yet. And one of the reasons is this is a bit more dangerous because a sealed gas is a lot more, like I said, dangerous than one that isn't. Because any fluctuation in temperature could create a pressure increase or decrease. For example, aerosol containers, great example. You never want to heat an aerosol container or throw a can of hairspray in a fire because when you increase the temperature so drastically, you may exceed the pressure rating for that container, especially if we're talking about a flammable gas, and there's plenty of those. So what I mean by that is you place an aerosol container inside a fire or a heated, environment, and you can really increase the pressure, and once that becomes high enough, there's no container in the world that is able to keep that in a sealed environment. It's going to blow the lid right off, cause an explosion, blah, blah, blah. We don't want that. So we'll get some more practice when we come back on Thursday. But I wanted you to be aware of the conditions where you would apply these gas laws. These three major gas laws really only apply for changing conditions, a before and after situation. The changing conditions generally are going to happen with any vessel that is closed. A piston where either the plunger is able to move up and down, a sealed plunger, a sealed balloon. It's going to really account for changing conditions in sealed environments that don't let things come in or out. And those sealed environments can vary depending on if the volume is either fixed or not. Temperature can be fixed as well. And we can do other things we'll learn later that also adjust how gases behave, such as the addition of more gas particles. Perhaps the addition of different gas particles. And so we'll investigate those a little bit more at a later time. But for now, the key understanding and the key concept is that we have three laws now that we have examined, either experientially or in a more conceptual way, that relate pressure, volume, and temperature. And what we're going to look at tomorrow is a completely different gas law that is going to incorporate all three components, and it's called the combined gas law. And it's a little bit more of an elegant and inclusive equation because it's going to account for these three major factors with any sealed container. And there's a lot of interesting application that's coming our way with the combined gas law. And the combined gas law is very similar. All that's really going to happen here is we're going to combine these three gas laws and make a new one, which is just the pressure, the temperature, and the volume. This isn't right. I got these things mixed up. Sorry, everybody. It's P1 V1 over T1 equals P2 times V2 over T2. And this is called the combined gas law. And again, we'll practice that more later. Right off the get, you will see that this is still a proportion. And so typically, the way that I like to operate and express this equation is a more user-friendly form to rearrange variables through simple cross multiplication. You guys are pretty good at math, you kind of understand that. So I will often display the combined gas law in its much more user-friendly form, which is this. P1 V1 T2 is P2 V2 times T1. So I prefer this iteration of that equation because it's easier to do simple algebraic manipulation if you're looking for a specific variable with changing conditions. So we'll pick this up when I see you guys next. Hopefully this is informative. Please answer the follow-up questions after the video. Thanks.